Good afternoon.
I like your time, Mr. Strong.
Well, I thank you. I appreciate that. I was going to save it for May the 4th.
Have a good day, Strong.
See you guys. Yeah, I was going to save it for May the 4th, be with you, but turns out that's on like a Saturday or something. So anyway, so that's no good. So you guys doing okay today? All right. So today looks like we're finishing up 10.5 and going on to 10.6. That's our plan. So either of you have any questions before we...
Yeah, I have a question actually. There's something I'm a little confused about.
Okay.
So, like in the problem we did yesterday, it was like 4 to the n plus 1, and then 4 to the n, and like they were on opposite sides, so they're in two different equations or whatever, and they're on opposite sides, so you're going to cancel them.
Right.
You subtract like the exponents, right?
Exponents. So you have 4n plus 1 minus 4n, so you're just left with 1. I mean,
Okay.
with 1 as your exponent, so it ends up being 4.
Okay.
So like here, so like if I have x to the n plus 1 divided by x to the n, when you cancel that, when you subtract the exponents, you just get x to the first. Or if I have 3 to the n plus 1 divided by 3 to the n, when you subtract the exponents, you just end up with 3.
Okay. Thank you.
Sure. Okay. So this is where I think we were at the root test. All right, so let's get that out. Okay, so, all right. Okay, so it says let is a sub n's be a series with a sub n is greater than or equal to 0. So, so the elements are positive, and suppose that the limit of the nth root of the a sub n's is equal to rho. Again, now, so we did this with the ratio test yesterday, and we got rho. And then this part right down here was exactly the same with the ratio test. That the series converges if rho is less than 1. The series diverges if rho is greater than 1 or infinite. And the test is inconclusive if rho equals 1. And so that's why we actually teach the ratio and the root test together, is because the way you interpret the test is exactly the same for each one. Okay, now, so what we need to get practice with here is taking the nth root. All right, so a couple of things here. One of the limits that we learned was that the nth root of n as n approaches infinity is 1. So that's going to be important. All right, and okay. So let's say we're trying to determine if n squared over 2 to the n diverges or converges. So what I'm going to do is use the root test. So the root test, okay. So what I do is, well, let's go. Sorry. Okay. So if I do the nth root of n squared over 2n, okay. Now look how this simplifies here. So we can split up the radical, so we're doing the nth root of both the numerator and the denominator. So now when we have the nth root of n to some power, you can bring the power out front or outside. And so when you have the nth root of n, this limit is just 1. So you get 1 squared, which is 1. The nth root of 2 to the n, well, this is like 1 over the power 1 over n times n. So their nth root and 2 to the n, those exponents are going to cancel. So you just end up with 2. So we end up with 1/2. All right, so then that's the row. So then you go back and you say, okay, if we get a row as 1/2, then it converges absolutely. So that means the series is going to converge. Okay. All right, so let's see if you can do practice 3. So now I've got it as 2n over n squared. So use the root test. All right, so Weston, what do you think?
I can't find my chapter 10.5 thing, so I don't have the rules exactly,
Okay.
but I got 2.
Okay. So if you get 2, then you as your row, then you go back and say, well, if row is greater than 1, then the series diverges.
Okay, yeah.
Okay?
Could you leave it on there real quick so I can
Sure.
write those down? Because I have
Yeah,
no idea
sure.
where my paper went.
Okay.
All right, thank you.
You bet. So you get, so the nth root of 2 to the n is 2. The nth root of n is 1, and then 1 squared is 1. So you get 2. 2 is greater than 1, so therefore the series diverges. Okay? All right. So now this says determine if the series converges or diverges. All right, so I'll give you a minute to think about this one. All right, Tobias, what do you think?
I got 1 at the end.
Okay. So you got 1. All right, let's take a look at that. So if you do the nth root test, okay, so you take the nth root of the whole thing. Well, then that's going to undo this n right here. And so then you just imagine taking this limit. So if you do that limit, what would you get?
1 over infinity.
Which is?
0.
0. So if your rho is 0, then what does that mean?
It means that it converges.
So the series converges. Okay? So if the rho is less than 1, the series converges. So that's a little different than like the nth root test. I mean the nth term test. You don't want to get 0. In the ratio test and the root test, you don't want to get 1. 1 is what makes it inconclusive. Okay? Now, with these tests, I'm not saying that it's a whole lot harder than that, but you do need some practice, and especially as we start mixing these things together on one sheet. So I would highly suggest that you do some of the practice problems, do some of the odd ones in the book, and see how it comes. If you can recognize the different tests that you would do. All right, now, but that's it for 10.5. We still have a couple of more tests to do in 10.6. All right, so 10.6, we're going to talk about alternating series and conditional convergence. Okay, these are both very important terms. All right, so the alternating series test, or Leibniz's theorem, I usually just call it the alternating series test, says if you have an alternator, okay, the -1 to the n, -1 to the n plus 1, all right, that causes the signs to alternate, right? So what you do is just sort of ignore the alternator and just look at the regular terms, okay? If these 3 things happen, then the alternating series will converge, okay? So these are the 3 things that you have to have happen, is that the terms without the alternator have to all be positive. So we call those the u sub n's. Okay? Secondly, the u sub n is greater than or equal to u sub n plus 1. What that means is that the series is getting smaller. Now, they can be the same, but they can't be getting bigger. And then finally, the u sub n's have to approach 0. Now, if all 3 of these things happen when you cover up the alternator, then that means the series will converge.
Mr. Strong,
Hey.
sorry I was late. I had an exam in my previous class.
Okay. Well, I'm glad you're here. So we finished up 10.5. So you might just want to, if we can get the videos to start posting, then yeah, it'd be worth it to look at that last little part. on 10.5, and then we just started 10.6. Okay, so let's look at an example here. All right. So, is this true? If a series converges, if I multiply that series by a constant, does it converge? What do you think?
Yes, it does.
Yeah, it does. Because see, if it converges to a number, here you're just multiplying it by a constant, and so it would just converge to a different number, but it would still converge. Okay? So that's going to be important. All right. So now let's look at this. Okay, so we want to know, does this series converge? Okay, now it has the alternator. So what you do is you cover this up. Cover the alternator up and just look at 1 over n. All right, and see if it satisfies the criteria. All right, so starting at 1, when n goes from 1 to infinity, are all the 1 over n's positive? Yeah, because you get 1 over 1, 1 over 2, 1 over 3. So again, we're not talking about the alternator. You just kind of ignore that. So all the u sub n's are positive. The terms are getting smaller. See, let's get rid of the... So 1 over 1, 1 over 2, 1 over 3, 1 over 4, each of those terms are getting smaller. Are they approaching infinity? I mean, 0, excuse me. Yeah, they're getting smaller and smaller. So that means this series converges. Okay? Now, this series actually has a name. This is the alternator, right? And this is the harmonic series, 1 over n. So this is called the alternating harmonic series. The alternating harmonic series. Now, what's kind of special about that is just the harmonic series diverges. But the alternating harmonic series, as we've just seen, converges. Because it satisfies these 3 conditions. Okay? All right. So let's have you look at practice 1 and see what you think about that. All right, Tobias, what do you think?
I got that it diverges.
Okay, let's see here. All right, so first of all, you notice it's an alternating series because it has the alternator. So when you cover that up and you look at this part, well, not all the u sub n's are positive. So it fails the test. It fails the test. Okay? So, now let's say that we bring the -1 out front. Okay? So this is -1 times a series. Okay? Now, if we cover this up, then let's think about 1 over n cubed. would 1 over n cubed be positive for all n? Yeah. Would they be getting smaller? Yes. Would 1 over n cubed go to 0? Yes. Okay. So then this will converge, and so -1 times that will converge. Okay. So, but just from the original problem, it basically fails the test. So whenever we do one of these tests and it fails the test, that doesn't mean that the other thing is true necessarily. Okay? So that's kind of the point of this problem, is that it just means it fails the test. So we don't know if it converges or diverges. Okay? We just know it fails the test. Okay? So then you try to do it another way, or like there, I just brought in put the -1 in front. Okay. All right. All right. Next, in the last section, we talked about absolute convergence. Okay. Yesterday, we said that if the absolute values converge, then it converges absolutely. And if it converges absolutely, then the series converges. Okay? Now, a series that converges but does not converge absolutely converges conditionally. Okay? Now, so this is the thing that you got to wrap your head around, because it's really easy to get this turned around here. If a series converges absolutely, then it converges in general. But if a series converges in general, that does not mean necessarily that it converges absolutely. It doesn't go back the other way. Okay? So, if a series converges but not absolutely, then it converges conditionally. So, the one that I think of in my brain is this alternating series. Okay? We just showed that the alternating series, when you cover this up, it actually passes the test. And so the alternating series, the alternating harmonic series converges. Okay? But if you take the absolute value, and so then that basically gets rid of this, and you just test this, okay, not with the alternating series test, but just in general, that's the harmonic series, and it diverges. Okay? So this is a series that this alternating series converges, but not absolutely. It does not, its absolute value doesn't converge. So we say that this converges conditionally. Oops. So it converges conditionally. So in my brain, next to the words converges conditionally, I have the alternating harmonic series. Because I know the harmonic series diverges, but the alternating harmonic converges. Okay? And so that kind of helps me keep it straight a little bit. And I know it's probably so this does not converge absolutely, it converges conditionally. Okay, where'd it go? Okay, so last section we learned that if the absolute value converges, So if it converges absolutely, it converges in general. Okay. All right. So when you have an alternating series, okay, then to test for absolute convergence, you test without the alternator. So it's like you're taking the absolute value. Okay. Or you can test for convergence using the alternating series test. So those three things, are all the u sub n's positive? Are they getting smaller? Do they go to zero? Okay. So you can do it one way or the other. Okay. So it just kind of depends on how you want to go about it. All right. So let's look at. Okay. So let's look at this one. It says determine if the series converges or diverges. Okay. So again, what we can do is ignore the alternator and just test this series. Or we can do the alternating series test. Okay. So let's just cover this up. And let's look at 1 over n to the 1/3. Does that series converge or diverge?
Diverges.
It diverges. Why?
Well, I don't know. I just remembered the P series.
It's a P series. That's all you need to say. It's a P
okay.
series, and P is less than 1. Okay? So P is 1/3. So this series diverges. Okay? So to say this series, so this series is not going to converge absolutely. All right? Now, to see if the series converges, then we can try the alternating series test. So again, we look at just this part and we say, okay, are all of these values positive? Cubed root of 1, 1 over cubed root of 1, 1 over cubed root of 2, 1 over cubed root of 3. Yes, they're all positive. Are they getting smaller? Let's see. Is 1 over the cubed root of 1 bigger than 1 over the cubed root of 2? And is that bigger than 1 over the cubed root of 3?
No.
No, because see, the cubed root of numbers are get bigger as the numbers get bigger. So these are getting bigger, but 1 over a bigger number is getting smaller. So these are getting smaller. Okay, but you have to understand that the cube roots are getting bigger, but since it's in the denominator, the whole fraction's getting smaller. Okay? Now, are these values going to 1 over the cubed root of n, are those approaching 0? Well, the cubed root of infinity is what? Cube root of infinity is infinity. And what's 1 over infinity? Goes to 0. Okay? So they are going to 0. So what does this mean? This means that from the alternating series test, this series converges. Okay? But when we did the absolute value, when we did away with this and just tried this, it diverged. So this converges conditionally. Okay? So it converged, but not absolutely. So that converged conditionally. Okay? Now, so this is just saying something that we've already done. This rearrangement theorem says we can always rearrange the terms of a finite sum. The same is true for an infinite sum that is absolutely convergent. So remember how when we were testing for convergence and we were looking for like clusters that would add up to 1 or add up to a half or whatever, and the clusters kept getting bigger? This is saying we can do that. That's a legal move, that we can rearrange the terms so that they can cluster together. Okay? So that's the rearrangement theorem. And so if we're trying to prove something's absolutely convergent, that's a legal move. Okay? All right, finally, the last thing I want to just kind of summarize here is, and we're not quite done with the test, but I like doing significant reminders of what we've done here. Okay? So this is how we've tested for convergence. Okay? So the first test that we did was the nth term test for divergent. And there what we did is we said if a sub n's approach 0, and then we don't know. Otherwise, the series diverges. Then there were some known series that we knew. So the geometric series, if the r is between -1 and 1, then it converges. Otherwise, it diverges. Then we have the p series. Okay, so let's see. Did we lose Jada? Are you still there, Jada?
Yeah, I'm here.
Okay, can you see me?
Yeah, I can see you. For a while, it was showing both of those screens, but
Okay.
it went back to you now.
Okay, so hopefully I can't see you right now, but it's been kind of coming and going all day. So hopefully that'll take care of it. We're almost done here. If you can see the screen here, this is kind of what we're ending on here today, is I'm just trying to summarize what we've done. Okay, so the P series. So Jada, you made me very happy when you remembered the P series. So 1 over n to the P converges if P is greater than 1. Otherwise, it diverges. All right, and then I kind of threw in 3.5. It helps if we know the harmonic series, 1 over n, diverges, whereas the alternating harmonic series converges. Then, for the series that had no negative terms, we learned the integral test, the ratio test, and the root test. And then we had 2 comparison tests. We had the term comparison test and the limit comparison test. Then series with some negative terms. Okay, that's where you think about get rid of the alternator. Look at the absolute value. If that converges, then it converges absolutely, and that means it implies that it converges in general. And then just now we did the alternating series test. So it converges if all the other terms minus the alternator are all positive, getting smaller, and approaching 0. All right, now I'm going to, I've got a little handout that once we finish the last, let's see, 6, yeah, I guess this is the last of the regular tests. We're going to do some different types of convergence next. But I'm going to go ahead and I've got a little handout that kind of summarizes this too. And I'm going to post the handout at the top of chapter 10. Okay? So it's like a summary of the tests that we'll do. So you could take a look at that and see if you have any questions on that. So today we finished up 10.5 and 10.6. And so we'll go to 10.7 tomorrow. But again, let me just stress what would be very helpful. These problems don't take a lot of time, but it really helps if you practice with the rules. So if you haven't practiced in each section, even if you just took 2 or 3 problems from each section and even mixed them up, created your own little worksheet, or just even if you wanted to focus on the integral tests or the alternating series tests or whatever, just do some of the practice problems. And I think you'll find it will start to click and these problems will seem much easier to you. It's just that when you first, now that you have all these tests before you, it can be kind of overwhelming. So just kind of practice on what you have, and I think you'll be fine. And then if there's one that that you don't understand, the back of the book says diverges, and you say you think it should converge or vice versa, then ask me to do it, and we'll go through it in class. Okay. All right, but this is a good time to stop. I don't want to start the next lesson yet. So, does anyone have any questions? All right, well, let's go ahead and call it for today. Thanks, you guys, and we'll see you tomorrow.